Hi, everyone, welcome to our workshop on zkSync project research. I'm excited to be your presenter today. We'll start with a brief overview of our agenda and what we aim to achieve in this session. Our objectives are to understand the concept of zkRollup and zkSync, explore the zkSync ecosystem, delve into smart contracts and code analysis, and finally discuss our research methodology and findings. Before we start, I'd like to talk about a vibrant and dynamic community called DoraDojo. DoraDojo is an open-source knowledge community focused on cutting-edge technologies such as encryption and Web3, co-built by hackers. DoraDojo regularly organizes and shares sessions in the form of live broadcasts, audio, and text. The topics covered include L1 and L2 consensus algorithms, architecture, and related content in GitHub repositories. Some of the specific topics covered include Scroll/Polygon zkEVM, Eigen's hybrid proof system, Starkware, Aztec, Optimism, zkRE, Aptus, Move, cryptography, including zero-knowledge proof, public key encryption, hash functions, and lattice ciphers, distributed systems, the Ethereum protocol stack, quantum computing and quantum information, and satellite communication and spacecraft system design. The DoraDojo community is constantly expanding and inviting new members to join. If you are interested in learning more about cutting-edge technologies and staying ahead of the curve, I encourage you to contact Dojo at DoraDojo0 on Telegram and claim your bounty. The dojo welcomes proposals for new content, and they will fund and share it. So, whether you are an experienced developer or just starting out, DoraDojo is the perfect community to learn and grow alongside like-minded individuals. Join us today and let's dive in together and explore the fascinating world of project research on zkSync, uncovering its groundbreaking technologies and potential impacts. Welcome to our zkSync workshop. We're going to dive deep into the zkSync project, exploring its technology, ecosystem, and future potential. Let me give you a brief overview of what we will cover in this session. By the end of this session, you'll have a comprehensive understanding of zkRollup and zkSync, their benefits, and their applications. Let's start by understanding the concept of zkRollup. zkRollup is a Layer 2 scaling solution for blockchains. It combines on-chain and off-chain processes to increase transaction throughput while maintaining security. Key principles include the use of zero-knowledge proofs to validate transactions, which offers significant technical advantages over other scaling solutions like Plasma or sidechains. These advantages include reduced gas fees and faster transaction times. Real-world applications of zkRollup include payment networks and decentralized exchanges. Then we talk about zkSync. zkSync is an implementation of zkRollup technology designed to enhance the Ethereum blockchain scalability. It enables faster and cheaper transactions without compromising security. Key features of zkSync include its user-friendly interface, seamless integration with existing Ethereum wallets, and robust security measures. This makes zkSync a promising solution for scaling Ethereum and other blockchain networks. Next, we dive into the zkSync ecosystem. The architecture of zkSync includes components like the zkRollup smart contract, the zkSync operator, and user accounts. The operational workflow involves users submitting transactions to zkSync, which are processed and aggregated off-chain before being validated on-chain using zero-knowledge proofs. This improves efficiency by reducing the computational load on the main blockchain, resulting in faster transaction processing times and lower costs. Moving on, let's explore zkSync's Layer 3 solution. Layer 3 builds on Layer 2 by providing even greater scalability and functionality. It introduces enhancements such as improved privacy features, more complex smart contract capabilities, and further reduced transaction costs. The potential for Layer 3 is immense, as it could enable decentralized applications to operate at a scale and efficiency comparable to centralized systems, which is crucial for the mass adoption of blockchain technology. zkSync smart contracts are crucial for the secure and efficient operation of the zkSync network. These smart contracts handle the validation of transactions and maintain state integrity. Key principles include trustlessness, allowing users to interact without intermediaries, and scalability, achieved through zero-knowledge proofs. Security is a top priority, with rigorous audit practices in place to identify and mitigate potential vulnerabilities. We will delve into the analysis of zkSync's open-source code. Our methodology involved a thorough review of the codebase to understand its architecture, security measures, and functionality. Key findings include the robustness of the zero-knowledge proof implementations and the efficiency of the transaction processing logic. Key findings include the robustness of the zero-knowledge proof implementations and the efficiency of the transaction processing logic. From here, our journey begins to delve deeper and deeper into more details. Let us begin. Welcome to our workshop on zkSync project research. In this session, we will cover several important topics. Let's start with a brief overview of our agenda and what we aim to achieve today. We will start by understanding the concept of zkRollup and zkSync, which are crucial for blockchain scalability and security. Then, we will explore the zkSync ecosystem to understand its components and how they work together. After that, we will delve into zkSync smart contracts, discussing their principles, functionalities, and security considerations. We will also analyze zkSync's open-source code, sharing key findings and insights from our research. Finally, we will discuss our research methodology, explaining how we conducted our study and presenting our findings. Our main objectives for this workshop are to understand the concept of zkRollup and zkSync. Explore the zkSync ecosystem and its components. Delve into zkSync smart contracts and code analysis. Discuss our research methodology and findings. By the end of this session, you will have a comprehensive understanding of zkRollup and zkSync technologies, their benefits, and real-world applications. Now, let's dive into the concept of zkRollup. This is a crucial technology for scaling blockchain networks, so it's important to understand how it works and why it's beneficial. zkRollup is a Layer 2 scaling solution for blockchains. It combines both on-chain and off-chain processes to increase transaction throughput while maintaining high levels of security. The zk in zkRollup stands for zero knowledge, which refers to the zero-knowledge proofs used to validate transactions. One of the key principles of zkRollup is its use of zero-knowledge proofs. These proofs enable the validation of transactions without revealing the transaction details. This approach offers significant technical advantages over other scaling solutions like Plasma or sidechains. Some of these advantages include: because zkRollup processes transactions off-chain and only posts the final proof on-chain, it significantly reduces the gas fees compared to processing each transaction on-chain. By aggregating multiple transactions into a single batch and validating them together, zkRollup can achieve much faster transaction times. zkRollup inherits the security of the underlying blockchain. The use of zero-knowledge proofs ensures that transactions are secure and verifiable. Real-world applications and examples. zkRollup is particularly beneficial in scenarios where speed and cost efficiency are critical. Some real-world applications include payment networks. zkRollup can be used to create fast and cost-effective payment networks, enabling quick transfers with minimal fees. Decentralized exchanges, DEXs can use zkRollup to process trades more efficiently, reducing costs and improving user experience. To give you a more concrete understanding, let's look at a simple example of how zkRollup works in code. Here is a basic example in Solidity, the language used for writing smart contracts on the Ethereum blockchain. In this simple example, we have a smart contract that represents the zkRollup. The contract has a state variable and an operator who is authorized to update the state. The update state function takes a new state and a zero-knowledge proof as inputs. It verifies the proof and updates the state if the proof is valid. The verify proof function is a placeholder for actual proof verification logic. This example demonstrates the basic idea of how zkRollup works. Off-chain transactions are aggregated and a single proof is submitted on-chain to update the state. In summary, zkRollup is a powerful Layer 2 scaling solution that combines the best of both on-chain and off-chain processing. It provides significant technical advantages, making it ideal for applications that require fast and cost-efficient transactions. Real-world applications of zkRollup include payment networks and decentralized exchanges, which benefit greatly from its capabilities. Now, let's talk about zkSync, a pivotal technology in the blockchain ecosystem. zkSync is a specific implementation of zkRollup technology, designed to enhance the scalability of the Ethereum blockchain. By leveraging the principles of zkRollup, zkSync combines on-chain and off-chain processes to achieve higher transaction throughput while maintaining robust security. The role of zkSync in the blockchain ecosystem is significant. It enables faster and cheaper transactions without compromising security, which is critical for the widespread adoption of blockchain technology. Ethereum, being one of the most widely used blockchains, greatly benefits from zkSync's capabilities, allowing it to scale efficiently and handle a larger volume of transactions. Let's dive into some of the key features and benefits of zkSync. 1. User-friendly interface. zkSync is designed with a focus on ease of use. It offers a user-friendly interface that simplifies the process of interacting with the Ethereum blockchain, making it accessible even for those who are not tech-savvy. Seamless integration. zkSync seamlessly integrates with existing Ethereum wallets, which means users can continue using their preferred wallets without any additional setup. This ensures a smooth user experience and encourages adoption. 3. Robust security measures. Security is a paramount concern in blockchain technology. zkSync employs zero-knowledge proofs and other advanced cryptographic techniques to ensure that transactions are secure and verifiable, maintaining the integrity of the blockchain. 4. Cost efficiency. One of the major benefits of zkSync is its ability to significantly reduce gas fees. By processing transactions off-chain and only posting the final proof on-chain, zkSync minimizes the cost associated with transactions, making it more affordable for users. Let's look at a simplified code example. Here's a basic example in Solidity, the language used for writing smart contracts on the Ethereum blockchain. Let's look at a simplified code example. Here's a basic example in Solidity, the language used for writing smart contracts on the Ethereum blockchain. In this example, the smart contract represents a simplified version of zkSync. Users can deposit funds into the contract, and their balances are tracked. When a user wants to withdraw funds, they must provide a zero-knowledge proof to verify the transaction. The verify proof function, in this case, is a placeholder for the actual proof verification logic. This example demonstrates how zkSync leverages zero-knowledge proofs to secure transactions and maintain a balance between on-chain and off-chain processing. In summary, zkSync is a powerful implementation of zkRollup technology that plays a crucial role in scaling the Ethereum blockchain. Its user-friendly interface, seamless integration with existing wallets, robust security measures, and cost efficiency make it a promising solution for the future of blockchain technology. Now, let's dive into the details of how the zkSync ecosystem works. Understanding its architecture and operational workflow is key to appreciating its benefits and efficiency improvements. Detailed architecture and components. The architecture of zkSync includes several crucial components. 1. A zkRollup smart contract. This is the core component that resides on the Ethereum mainnet. It is responsible for storing the compressed transaction data and ensuring the security and integrity of the off-chain data. 2. zkSync operator. The operator is responsible for aggregating transactions submitted by users, generating zero-knowledge proofs for these transactions, and submitting these proofs to the zkRollup smart contract for validation. 3. User accounts. Each user has an account within the zkSync ecosystem where they can deposit and withdraw funds, as well as initiate transactions. Operational workflow and transaction processing. The operational workflow of zkSync involves several steps. 1. Transaction submission. Users submit their transactions to the zkSync operator. These transactions can include payments, token transfers, or other smart contract interactions. 2. Off-chain aggregation. The zkSync operator aggregates multiple transactions into a single batch off-chain. This significantly reduces the number of transactions that need to be processed on-chain. 3. Zero-knowledge proof generation. For each batch of transactions, the zkSync operator generates a zero-knowledge proof that verifies the validity of all transactions in the batch without revealing the transaction details. 4. On-chain validation. The zero-knowledge proof is then submitted to the zkRollup smart contract on the Ethereum mainnet. The smart contract validates the proof, ensuring that all transactions in the batch are correct. 5. State update. Upon successful validation, the state of the zkRollup is updated on-chain, reflecting the outcomes of the processed transactions. Benefits and efficiency improvements. This architecture and workflow offers several key benefits and efficiency improvements. Faster transaction processing. By processing transactions off-chain and only submitting the final proof on-chain, zkSync achieves much faster transaction processing times compared to on-chain processing. Lower costs. The aggregation of transactions into a single batch significantly reduces the gas fees associated with individual transactions, making it more cost-efficient for users. Enhanced scalability. zkSync improves the scalability of the Ethereum network by reducing the computational load on the main blockchain, allowing it to handle a larger volume of transactions. To illustrate this process, let's look at a simplified example of zkSync's operation in code. Here is a basic example in Solidity. In this example, the smart contract represents a simplified version of zkSync's operation. Users can deposit funds into the contract, and their balances are tracked. When a user wants to withdraw funds, they can do so, provided they have a sufficient balance. The submit batch function allows the operator to submit a batch of transactions along with a zero-knowledge proof. The verify proof function is a placeholder for the actual proof verification logic. This example demonstrates how zkSync leverages zero-knowledge proofs and batch processing to improve efficiency and reduce costs. In summary, zkSync's architecture and workflow provide a robust solution for scaling Ethereum by enabling faster and cheaper transactions while maintaining high security. The benefits of this approach are evident in its ability to handle a large volume of transactions efficiently, making zkSync a vital component of the blockchain ecosystem. Moving on, let's talk about zkSync's Layer 3 solution. This is an exciting development that builds upon the success of Layer 2 solutions to provide even greater scalability and functionality. To start with, what is Layer 3? While Layer 2 solutions, like zkRollups, have significantly improved the scalability of blockchain networks by moving transaction processing off-chain, Layer 3 aims to take this a step further. Layer 3 solutions are designed to provide an additional layer of scalability and functionality, enabling more complex operations and greater throughput. Layer 3 can be thought of as an additional abstraction layer on top of Layer 2. This means that while Layer 2 focuses on scaling transactions and reducing costs, Layer 3 focuses on enhancing the capabilities and efficiency of decentralized applications, or dApps, built on these scaled networks. Technical enhancements provided by Layer 3. Let's delve into some of the technical enhancements that zkSync Layer 3 brings to the table. 1. Improved privacy features. One of the key enhancements is the improvement in privacy features. Layer 3 solutions can provide advanced privacy techniques such as confidential transactions and anonymous smart contracts. This ensures that sensitive information is kept private while still benefiting from the scalability and security of the underlying layers. 2. More complex smart contract capabilities. Layer 3 allows for more complex smart contracts. This is crucial for developing sophisticated dApps that require intricate logic and functionalities. With Layer 3, developers can build smart contracts that were previously too complex to be efficient on Layer 2. 3. Further reduce transaction costs. By offloading even more processing from the main blockchain and Layer 2, Layer 3 can further reduce transaction costs. This makes it economically viable to perform a higher number of transactions, which is essential for the mass adoption of blockchain technology. Future potential and scalability. The potential of Layer 3 is immense. It could enable dApps to operate at a scale and efficiency comparable to centralized systems. which is crucial for the mass adoption of blockchain technology. Here are some future potentials. Mass adoption of dApps. Layer 3 makes it feasible to run highly scalable and efficient dApps, attracting more users and developers to the blockchain ecosystem. This could lead to a wide array of decentralized services becoming mainstream. Enterprise solutions. Layer 3 scalability and advanced features make it suitable for enterprise solutions. Businesses can leverage these capabilities to build robust and efficient blockchain-based applications that meet their complex requirements. Ecosystem growth. As Layer 3 solutions mature, they will contribute to the overall growth of the blockchain ecosystem. This includes not just the increase in the number of dApps, but also the enhancement of user experience and the expansion of blockchain use cases. To illustrate this, let's look at a simple example of how zkSync Layer 3 might be implemented in a smart contract. In this example, we have a smart contract that includes a confidential transfer function, demonstrating an advanced privacy feature that Layer 3 could support. Users can transfer funds with an additional encrypted data field, enhancing privacy. In summary, zkSync Layer 3 is a groundbreaking advancement that builds on the success of Layer 2 solutions, providing improved privacy, more complex smart contract capabilities, and further reduced transaction costs. Its potential to enable dApps to operate at scale and efficiency comparable to centralized systems is crucial for the future of blockchain technology. By leveraging Layer 3, we can unlock new possibilities and drive the mass adoption of blockchain applications. Next, let's delve into the principles of zkSync smart contracts. These smart contracts are fundamental to ensuring the secure and efficient operation of the zkSync network. They manage the validation of transactions and maintain the integrity of the state. zkSync smart contracts operate on the Ethereum blockchain and utilize zk rollup technology to process transactions. They play a crucial role in aggregating multiple off-chain transactions into a single on-chain transaction, thus optimizing performance and reducing costs. There are several key principles and functionalities that make zkSync smart contracts unique and effective. 1. Trustlessness. One of the core principles of zkSync smart contracts is trustlessness. This means that users can interact with the system without needing to trust a central authority. Instead, the system relies on cryptographic proofs to ensure the validity and integrity of transactions. 2. Scalability. zkSync smart contracts achieve scalability through the use of zero-knowledge proofs, zkSNARKs. These proofs enable the network to validate large batches of transactions off-chain and then commit a single proof on-chain. This significantly reduces the load on the Ethereum mainnet and allows for higher transaction throughput. 3. Efficiency. By aggregating transactions off-chain, zkSync smart contracts improve efficiency. Users benefit from faster transaction times and lower fees, making the system more practical for everyday use. 4. Security. Security is paramount in zkSync smart contracts. They employ advanced cryptographic techniques to ensure that transactions are secure and tamper-proof. This includes the use of zkSNARKs to validate transactions without revealing sensitive information. Given the critical role of security in blockchain applications, zkSync smart contracts are subject to rigorous audit practices. Here are some key security considerations. 1. Regular audits of the smart contract code are performed by independent security firms. These audits aim to identify and mitigate potential vulnerabilities in the codebase. 2. zkSync employs formal verification methods to mathematically prove the correctness of the smart contract logic. This helps ensure that the contracts behave as intended under all possible conditions. 3. zkSync has a bug bounty program that incentivizes external security researchers to find and report vulnerabilities. This crowdsourced approach helps uncover issues that may not be identified during regular audits. 4. The smart contracts are continuously monitored for unusual activity or potential security threats. This proactive approach allows for quick responses to emerging risks. To illustrate these principles, let's look at a professional example of a zkSync smart contract in Solidity. In this professional example, the smart contract includes Deposits and withdrawals. Users can deposit Ether into the contract, which is tracked in their balance. Withdrawals require a signature from the zkSync operator, ensuring that only authorized withdrawals occur. State updates. The zkSync operator can update the state of the contract by submitting a batch hash and a new state root. This represents the aggregated off-chain transactions being committed on-chain. Security. The use of ECDSA signatures ensures that only the authorized operator can approve withdrawals, adding an extra layer of security. This example demonstrates how zkSync smart contracts leverage trustlessness, scalability, efficiency, and security to provide a robust solution for blockchain scalability. In summary, zkSync smart contracts are a pivotal component of the zkSync network, ensuring secure and efficient operation through principles of trustlessness, scalability, efficiency, and rigorous security practices. By employing advanced cryptographic techniques and continuous security audits, zkSync smart contracts maintain the integrity and reliability of the network, driving the future of scalable blockchain solutions. Next, let's delve into the analysis of zkSync's open-source code. This analysis helps us understand the underlying architecture, security measures, and functionality that make zkSync a robust and efficient scaling solution for Ethereum. Our code analysis followed a systematic methodology to ensure a comprehensive understanding. 1. Codebase review. We started with a thorough review of the zkSync codebase available on GitHub. This involved examining the main components, their interactions, and the overall architecture. 2. Security assessment. We focused on the security measures implemented in the code. This included analyzing the use of cryptographic techniques, such as zks and RKS, and other security practices. 3. Functionality testing. We tested the functionality of the smart contracts and other components to understand how transactions are processed, validated, and committed. Finally, we evaluated the performance aspects, particularly the efficiency of transaction processing and the impact on gas fees. Our analysis yielded several key findings and insights. 1. zkSync's use of zero-knowledge proofs, specifically zks and RKS, is highly robust. These proofs ensure that transactions can be validated without revealing sensitive information, maintaining privacy and security. 2. The transaction processing logic in zkSync is highly efficient. By aggregating multiple transactions off-chain and submitting a single proof on-chain, zkSync significantly reduces the computational load and gas fees. 3. The architecture of zkSync is designed for scalability. The separation of on-chain and off-chain processes allows the system to handle a large volume of transactions without compromising on performance. 4. Security is a top priority in zkSync. The code includes several layers of security, from cryptographic proofs to formal verification methods, ensuring that the system remains secure against potential attacks. To illustrate these points, let's look at some specific code snippets from the zkSync codebase. Here is an example that shows how zkSync handles transaction validation using zkSnarks. In this example, the zkSync transaction validator contract uses a zkSnark verifier contract to validate transactions. The validate transaction function takes a transaction hash, a zero-knowledge proof, the user address, and the amount. It verifies the proof and, if valid, updates the user's balance and emits a transaction-validated event. Another important aspect is the aggregation of transactions. Here's a simplified example of how transactions might be batched and a proof generated. Another important aspect is the aggregation of transactions. Here's a simplified example of how transactions might be batched and a proof generated. In this example, the zkSync batch processor contract handles the aggregation of transactions. The submit batch function aggregates the transaction hashes into a single batch hash and verifies it using a zero-knowledge proof. Only the zkSync operator can submit batches, ensuring controlled and secure processing. In conclusion, our analysis of zkSync's open-source code reveals a well-architected, secure, and efficient system. The use of zero-knowledge proofs, efficient transaction processing, and comprehensive security measures make zkSync a standout solution for scaling Ethereum. These findings highlight the robustness of zkSync and its potential to significantly enhance the scalability and usability of blockchain networks. This detailed examination of the codebase underscores the importance of open-source contributions and transparency in building trust and advancing blockchain technology. By continuously improving and auditing the code, zkSync remains at the forefront of innovation in the blockchain space. Let's discuss our research methodology, which played a critical role in ensuring that our findings on zkSync are both well-informed and reliable. Our approach began with a comprehensive review of existing literature on zkRollup and zkSync. This included: we delved into various scholarly articles and papers that provided theoretical and practical insights into zkRollup technology and zkSync. These papers helped us understand the underlying principles, technical challenges, and potential solutions associated with these technologies. The official documentation of zkSync and related technologies was a valuable resource. It provided detailed information on the implementation specifics, smart contract architecture, and the cryptographic methods used, such as zkS and RKS. We reviewed industry reports and white papers that discussed the broader impact and adoption of zkRollup technology within the blockchain ecosystem. These reports offered a macro perspective on how zkSync fits into the larger picture of blockchain scalability solutions. We included diagrams and charts to illustrate key points. For example, we used flowcharts to depict the transaction validation process and graphs to show gas fee savings achieved through zkSync. Let's summarize the key points we've covered today to ensure we have a clear understanding of zkSync and its importance in the blockchain ecosystem. We began with an overview of zkRollup and zkSync. We discussed how zkRollup serves as a Layer 2 scaling solution that enhances blockchain throughput by combining on-chain and off-chain processes. zkSync, as an implementation of zkRollup, leverages zero-knowledge proofs to validate transactions efficiently and securely. This combination reduces gas fees and accelerates transaction times, making it a crucial technology for scaling Ethereum. Next, we explored the zkSync ecosystem. We delved into its architecture, examining components such as the zkRollup smart contract, the zkSync operator, and user accounts. We also discussed the operational workflow, which involves the off-chain aggregation of transactions and on-chain validation using zero-knowledge proofs. This workflow enhances scalability and reduces costs. We then introduced zkSync's Layer 3 solution, which builds upon Layer 2 by offering even greater scalability and functionality. Layer 3 provides advanced privacy features, more complex smart contract capabilities, and further reduced transaction costs. These enhancements make zkSync's Layer 3 solution a powerful tool for enabling decentralized applications, dApps, to operate at scale, fostering the mass adoption of blockchain technology. We also analyzed zkSync's smart contracts, emphasizing their principles and security measures. We discussed how zkSync smart contracts ensure trustlessness and scalability through the use of zero-knowledge proofs. The security of these contracts is maintained through rigorous audit practices, formal verification, and continuous monitoring. These measures are vital for protecting the integrity of the system and ensuring that transactions are processed securely and efficiently. Lastly, we discussed our research methodology. Our comprehensive approach involved reviewing academic papers, technical documentation, and industry reports. We conducted additional studies by analyzing blockchain data and consulting with experts. This thorough approach ensured that our findings are well-informed and reliable. Our findings highlighted the robustness of zkSync's zero-knowledge proof implementations, the efficiency of its transaction processing logic, and the comprehensive security measures in place. In conclusion, zkSync is a groundbreaking technology that significantly enhances the scalability and efficiency of the Ethereum blockchain. Its robust architecture, innovative use of zero-knowledge proofs, and advanced Layer 3 solutions position it as a leading solution for scaling blockchain networks. The insights from our research underscore the potential of zkSync to drive the future of decentralized applications and the broader blockchain ecosystem. Before we conclude, I'd like to provide a list of references and additional resources that we used for this presentation. These materials will offer you a deeper understanding of zkSync and zkRollup technologies. Here list of all referenced materials. But Aaron, v. 2019, An Incomplete Guide to Rollups. This article provides an excellent introduction to rollup technologies, including zkRollups. It outlines the technical fundamentals and potential benefits. 2. Ben Sasson 2014, Scalable Zero Knowledge via Cycles of Elliptic Curves, a seminal paper on zero-knowledge proofs that underpins much of the zkSNARK technology used in zkSync. 3. Matter Labs, 2021, zkSync Documentation, the official documentation for zkSync, providing detailed technical information about its architecture and operation. 4. Gudgeon, 2020, The Cost of Decentralization in 2020, Quantifying the Performance Cost of Ethereum's Decentralization. This paper discusses the scalability challenges of Ethereum and how solutions like zkRollups can address these issues. 5. Ethereum Foundation, 2021, Ethereum 2.0 and Scalability. This report covers the broader scalability initiatives for Ethereum, including Layer 2 solutions like zkRollups. 6. Bo, 2017, zcash Protocol Specification. While focused on zcash, this document provides detailed insights into zks and RKS, which are also integral to zkSync. And final Binance Research, 2021, Layer 2 Scaling, a comprehensive analysis. This report provides a comprehensive analysis of various Layer 2 scaling solutions, including zkRollups and zkSync. Thank you all for your attention and participation today. I hope you found this session informative and engaging.